Hello. 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 All right, are you seeing stuff? All right, I got this to work. Okay, folks, I need your questions. What do you want me to go over? All right, so you have to let me know if there's any issues as we go along, as it's the first time I'm using this. Okay. All right, so can you see the sheet here? All right, so what we're trying to do here is to find the derivatives of trigonometric functions. All right. So if you see what I did is I just applied the limit definition to the sine function. All right. And essentially I try to do exactly what I did before, is try to do some sort of algebra to solve this limit. All right. Because I do see that it's an indeterminate form. So the only thing I have access to here is to use my trig identity. So that's what I do. I go on to the next step, and you see that I just applied the trig identity for the sum, the sine of a sum. All right, nothing special here. So again, I'm looking for some more algebra to do, and so this is where I notice the sine x is common to the first and last term. All right, so I just factor out the sine x, and I end up with this thing here. And this is where we end up with a problem, is there's not really much else we can do. Okay, because we can't split up anything else. So this is where we have to start being a little clever. So the idea is to try to get all the h's together, all right, and also to notice that this sine x and this cos x with respect to the limit are just constants. Okay, so that's what I do next. I play around with things a little bit. I divide out the h to both terms in the numerator, and next thing you know, I end up with this here. All right. So what I do is I ask myself, well, can I split up this limit like we used to do in the past? So again, sine x, cos x, just constants. So I've got this addition. So I consider applying this addition rule plus the constant multiple rule for the limits, but that only works if these limits exist. All right. So that's the first thing we ask ourselves. Does the limit exist? All right. So next thing I do is I go to a graph of sine x, and I start graphing it like I did before. So I find the x-intercepts, and as you see here, as I start to graph the function, so if I take a look at this x-intercept and I looked at the function to the right, I saw that the slopes of the tangents were positive and getting larger. To the left, negative and getting smaller, so it would have come down here. So it's getting larger here. Oh, is this going too fast? Let me know if this is going too fast. And try to use words because I don't understand your symbols. All right. So how many people Give me a 1 if you already watched the video. Okay. So let me give me a second here. Well, folks, if nothing else, this is exciting. Ah, thank you. See, we'll just adapt as we go along. All right. Let's start from the beginning. How about that? Agreed? Yes, start from the beginning. Okay, all right, so let's start from the beginning. So let me try to slow down so that we can keep up with the delay. So we're trying to find the derivative of sine x. All right, the best thing to do would be to use the limit definition so we can actually prove that what we come up with is indeed the derivative of sine x. All right, so that's going to be our starting point. So starting point is just applying the limit definition. So limit as h approaches 0 of sine of x plus h minus sine of x over h. All right, so all I did here was to apply the definition of the derivative to this particular function. All right. Now, in the past, what we would do is we would try to do some algebra in the numerator and eventually end up with a factor of h that I would then reduce with the h in the denominator. All right. So let's try to do the same thing. The question is what kind of algebra can I do with sinusoidal functions? And what I have here are my identities. That's really all I have at my disposal. So the first thing I'm going to do is I'm going to apply the sine of a sum identity and see where I can go. So how does that work? Well, it's sine of the first times cos of the second plus sine of the second times cos of the first. All right? And then, of course, I have the minus sine x. And all this over h. All right, so what's the next thing we can do? I do notice that there's a sine x that's common to both the first and last term. So let me go there and factor that out. All right, so from the first and third term, I factor out a sine x. And what am I left with? I'm left with cos h here. And then here I'm just left with a minus 1. All right. And then here I'm left with the sine h cos x all over h. All right. Any questions before I move on? Okay, I'm not seeing any questions, so I'll assume that I can move on here. All right. Good. Okay, so this is where we hit an impasse because there's not really much we can do at this point. All right, so what we're going to try to do is try to rearrange this to see if I can get it in a nicer form, something I can at least work with. All right, so the first thing I notice is that my limit has h approaching 0. Sine x and cos x are unaffected by h approaching 0. So within this limit, sine x and cos x, whatever the x value is, behave like constants. All right, and the other thing I have here is an addition. So I'm going to do what we did with the proof of the addition formula. and at some point with the proof of the product rule, is I try to split this up into smaller limits. Okay, hopefully things that I can deal with a little better. Okay, so first thing I'm going to do is divide out the h to both terms. Okay, and I'm going to keep everything with h all together. So I'm going to keep the sine x separate, and then together I'm going to keep the cos h minus 1 over h. All right, and then here, when I divide the h to that one, I'll keep the sine h and the h together times cos x. All right, and the idea is to now use my limit properties to rewrite this as separate smaller limits. All right, so I'm going to use the addition rule. All right, and here I don't really have to use the product rule because sine x, remember, acts like a constant, and the limit of a constant times a function is just the constant times the limit. All right, so I'm going to rewrite this as sine x, okay, times the limit as h approaches 0 of cos h minus 1 over h. All right, plus cos x, which again acts like a constant, times the limit as h approaches 0 of sine h over h. All right, except I really need a question mark here because this doesn't always work. This only works if all the limits exist. All right, so this only works if the limits exist. All right, so here are my limits. Do these limits exist? So while I wait for any questions, you can, well, look at that, Mr. Oscar Dunkley. What the hell are you doing here? Okay, so I want you to think about that. If you have any questions, let me know before we go on and keep talking about that. Hey, Oscar, how's it going? We didn't have this last year, did we? All right, so I don't see any questions, so let's start talking about these limits here. Well, we're going to take a look at them in a second, but what we're going to do is take a different approach because we kind of hit a roadblock when it came through the using the limit definition. So this is where now we're going to use the graphical approach to see if that takes us anywhere. Okay, so what I'd like you to do is, while I'm talking a little bit, I'd like you to start filling out the information on this graph in order to draw the derivative given the graph of the function. Okay, so first thing you should be doing is putting points anywhere this function has a horizontal tangent. All right, horizontal tangent means the derivative is going to have an x-intercept there. So we have lots of x-intercepts. So next thing we have to do is figure out how this thing is going to behave. So I take a look at this 0 here, and to the right I see that my slopes are positive and getting larger. So I know my derivative function is going to be going upwards here. And then at some point, and seems to happen around here, the slopes are still positive but are getting smaller. So at some point they're going to come back down. Okay, and then eventually they'll go negative. But in the past, when we did this, we were just trying to get a sense of the shape of the graph. We want to be a little more precise now. Okay, so it seems to be that around 0 is where it goes from increasing slopes to decreasing slopes. All right, so we're going to actually try to estimate what that largest slope is to help us draw a better graph. So this is where, you get your trusty ruler out and you place it and try to draw the best tangent you can. All right, and so here, let's try to draw a tangent line. And that looks pretty good. and let's find the slope of that line, because we're conjecturing that this is going to be the steepest of the tangents. All right, so we look here and we see, well, it passes through 0, 0, obviously, and we see that as x goes up by 1, y goes up by 1. So in other words, this has a slope of 1. So at this point here, slope of the tangent is going to be to 1, and that's the largest of them all. So what's happening? The derivative is going up to this point here, and then it's coming back down to that point there. Okay, if you take a look at this point where it seems to go from, here it goes now to the negatives, and they're getting more and more negative, more and more negative, and around this point it seems to start getting less and less negative as they become less steep. Okay, but because of the repetition of the sine function, we can conjecture that whatever the slope of the tangent is here, the slope here would just be the negative of that. And if you want, you can draw yourself a line and find an estimate for the slope, and you'd see that it would be, at least look really close to negative 1. So at this point here, slope of the tangent is equal to negative 1. So it goes down to here and then back up to there. And then things start to repeat themselves, because now I'm going back to the positive, getting steeper, steeper, steeper. This is going to be my steepest slope, which again is just going to be a repetition of the one that we had here. So at this point here, going to positive 1. And if you take a look, what do we have? We seem to have that f prime of x is equal to cos x. Okay, and that's a pretty nice result. Now, we shouldn't be surprised that the derivative is periodic, because if sine x repeats itself, it means those slopes of the tangents are going to repeat themselves. But this is a pretty nice result that it's exactly the function cos x. All right, so before I take a little break here, we need to understand now why working in radians is so much better than working in degrees when we start working with trigonometric functions. Because imagine what the sine function would look in degrees with these units here. It wouldn't reach its maximum till 45. Till 90, which is very, very far away. So there's no way that the slope of the tangent at 0 would be equal to 1 if we were working in degrees. All right, so now we're starting to see the big reason why we work with radians as much as possible when we're working with trigonometric functions. All right, so I'll just wait a couple of seconds, and you let me know if you have any questions on this. Sorry, Felix, no shout out. All right, so let's now take this and go back to where we were at and see if that can give us some some inspiration for these limits here. All right, so our conjecture is that this derivative is going to give me cos x. Okay, now, by the way, one thing we didn't talk about these limits is, do they even have a chance at existing? Because if you look at the denominators, they're both approaching 0. So these need to be indeterminate forms in order for the limit to even possibly exist, and we see that they are. Because what does sine h approach as h gets closer to 0? Well, sine of 0 is just 0. And what does cos h minus 1 approach as h approaches 0? Well, cos of this 0 is 1, minus 1 is 0. So yeah, these are both indeterminate forms. But what do we need these limits to be equal to? Well, this is where I don't want this sine x in my final answer. So I'm really hoping that this limit is equal to 0. Okay, I do want this cos x around, but I don't want it to have any coefficients. So I'm really hoping that this limit is equal to 1. Okay, and what we're going to see in a couple of seconds is that okay, it seems every one of my old students is showing up here. Hi, guys. So we're going to see that these limits make sense. Now it turns out that this is the only one we actually need. Tomorrow in class, what we're going to see is that I can use this limit to prove that that limit has to be equal to 0. So everything we do, absolutely everything we do related to derivatives of trigonometric functions all hinge on this single limit. Okay, so it's pretty powerful that one limit can do all that for us. And this is a limit that's not that difficult to prove algebraically. Okay, I'd say maybe a little beyond our course, but not that far off. Okay, but we are going to look at it geometrically to see that it makes perfect sense. Okay, and in fact, I kind of have my answer in this diagram here. All right, so think of this as the function sine x over x as x approaches 0. Okay, just using a different variable because that's what I have graphed here. Take a look at sine x and take a look at this function here, which, hey, has a slope of 1 and passes through 0, 0. So this line here just represents the line sine x. Y equals x. And look at what happens near 0. Okay, you realize that these two functions near 0 are indistinguishable from each other. And we're taking the limit as h approaches 0. So when h is very close to 0, these two numbers are almost exactly the same. In fact, the closer you get to 0, the closer these two numbers get. And what happens when you divide two numbers that are very close? You get something very close to 1. Okay, so in fact, let's take a look at a graph here. So just to be sure, if I take a look at this graph of sine x, okay, and now I graph x, and look at what we have here. As I zoom in, we see that the closer I get to 0, okay, the function y equals x and the function y equals sine x become almost indistinguishable. Okay, we're actually going to talk about this in class because this has some pretty big implications. Okay, so looks like we're being asked for a break. Matthew, is that what I'm understanding? Aiken, try to put your mind back together there. We need it for tomorrow. All right, I'm just going to keep going. No, I was stating that it was an intermission. Oh, okay. Not sure what that means, but I'll just keep going. Okay, so we see here that okay, I get it. All right, folks, let's look here. So we have that sine x over x approaches 0 as x approaches 0, so that's good. In fact, if we even graph here, we can actually graph the function sine x over x. So here we got sine x and then divided by x. Okay. Now obviously this function should have a hole there, it doesn't show, but you see that if we approach it from the left and we approach it from the right at 0, we see that it's approaching 1. All right. So while this is not a proof that the limit of sine x over x approaches 0 as x approaches 0, it's a fairly nice graphical argument that we're making. Okay, and in fact we can go further. Okay, because let's take a look at that other one that we're hoping is going to be giving us what we need. So remember what we said we wanted is we wanted the limit of cos x minus 1 over x to be approaching 0. Okay, so let's see if that makes sense. So here I have the function cos x minus 1, so just cos x brought down by 1 unit, and here we have the function y equals x. And we notice that as x approaches 0, they're both approaching 0. What's the trick here? cos x minus 1 is approaching 0 much, much faster than y equals x. Okay, so here we can conjecture that the numerator starts to take over. It's approaching 0 much quicker than that one there, so the whole function should be approaching 0. Okay, and if we want to confirm that, let's graph cos x minus 1 over x. So here we've got cos x minus 1 all over x. And we see that as we approach 0 from both the left and right, that function does approach 0. Okay, so again, that seems to justify, that seems to justify our conjecture here that we made. So in the end, what do we have? We have that the derivative of sine x is equal to cos x. Okay, I think we have enough proof here, or not proof, wrong word to use, but I think we have enough evidence to be fairly certain about this one here. Okay, so in tomorrow's class, we're going to see how we can use this limit, that sine h over h approaching 0 is equal to 1, how we can actually use that to prove this other limit. So again, all this stuff we're doing all hinges on this one single limit. Okay. So I think what I'm going to do is I'm just going to stop for 5 minutes, let people think about this, see if you have any questions, and we're going to come back and do page 2. Okay, so I'm going to turn things off for a couple of minutes here. Okay, I'll be back soon.